Hi, I'm David Byte, and today we're going to talk about architecting Ceph solutions. We're going to really start with identifying the purpose of solutions from SUSE, and then we'll move into the process and then discuss some key considerations and rules of thumb. So these solutions are important because our customers often find it difficult to stay up to date with the latest in the technology landscape, and SUSE is in the job of providing infrastructure solutions. So these customers will look to us and our partners for guidance on what solutions they should implement and how they should implement those to improve their infrastructure. So a solution design from SUSE is intended to provide a roadmap to a successful architecture and implementation. In other words, the best documents from us are implementation guides, giving you very specific guidance on how we get from point A, which is 0, to point C, which is a deployed solution. For storage, they should outline key architectural decisions that the customer has to make along the way. And we should talk about the implementation process used to achieve this solution. So the solutions really talk about the building blocks for success. So when we start, we usually want to start with YES certified hardware. YES is the certification program that SUSE puts vendor hardware through. This gives us a level of confidence that the hardware is stable and operates correctly. And then obviously the next building block are SUSE products. And then the final piece are implementation guides. With these three things together, any partner or customer should be able to take the SUSE products, the hardware, and the implementation guide and come out with a successful implementation. So let's talk about the process. So I kind of see this as a 6-step process. There's a lot of things to this, but they're pretty common sense. The first thing we have to do is really identify the challenge we're trying to solve, whether it's be able to provide a heterogeneous backup environment, a backup solution that can scale to the exabytes, or we're trying to provide a data lake, or maybe high performance computing storage. So that's trying to understand the challenge. Is it a problem of scale? Is it a problem of performance? Is it a problem of cost or stability? What are those challenges right there? So that leads us into the requirements. And when we start talking about requirements, this is taking those challenges and bringing them down to measurable items. And the requirements could be things like capacity, performance requirements, ability to deal with certain I/O patterns, data protection schemes, client access methods, security. Those are all things that feed into the requirements. So the next thing that I would do is draw a solution idea, a straw man, and look at this and discuss it with fellow architects. This gives us a good ground to look at an idea, poke holes at it, try to see where it may have strengths, where there may be weaknesses that we need to think about and address. Once this process is done, we've gone through some revisions usually, we'll come up with a finalized design. This design is what we start the document with. We now have the idea that we want to get across to you as the customer, and that becomes the basis for the solution design. The next thing we'll do is we'll actually implement the design, and along the way we document the implementation process and the results. This is so that we have that step-by-step guide that occurs, right? So this is the good idea of a process. So when we go to implement the design, this is where things start getting sticky and somewhat difficult at times. It requires hardware. Software we've got, but the hardware can be hard to come by. It requires expertise. If it's something that I don't have an expertise in, which there are many topics, we need to pull in somebody who has it. Recently we did some work with Splunk. I am not a Splunk expert, so we had somebody that is participate in the project and helped us do a proper implementation so that we can then document it and release that document. It does require time, and it requires testing. Now these last two go hand in hand. The time also with hardware. Sometimes getting access to hardware means we have to work with a vendor partner, and it may take weeks or maybe even months in some cases to get access to the right pool of equipment. And then we have to have our time allocated and planned so that we can quickly jump into the process of building, installing, deploying, and testing, and documenting that process, right? So this takes a while. And the testing also involves a few things. When we're doing just a straight hardware implementation, we like to do a baseline benchmark. What does an out-of-the-box install, how does it perform? And provide that data in the back of the reference guide if the cluster meets the minimum cluster size that SUSE supports. Outside of that, it requires testing the documented steps. So this is where we take the document, we wipe everything out back to zero, start over, and walk through the document again to make sure that it all works as advertised. So let's talk about some key considerations. The first thing is to know what is important, because these are things we need to draw out in the solution design. Does it require performance, geographic redundancy? Is it a low latency performance requirement or a high throughput requirement? What does it look for? Are there specific features that the solution needs to rely on? Like, does it need to leverage the multi-site object gateways that we have? Does it need to utilize snapshots? What are the key features that need to be called out that bring value to the solution? And that's where we get into the key differentiators. What does this solution provide that makes it unique and important to our customers? That has to be drawn out in the document. And then there are some situations, like say perhaps a backup environment, where an out-of-the-box configuration is sufficient. It doesn't require performance tuning. But there are others, like the media and entertainment paper I worked on in last year that was published in late October, that required a significant amount of performance tuning. And then do parts of the implementation need to be scripted? If we're having to deal with setting up a lot of software, bringing in a lot of libraries and things that aren't part of the standard build, it may be easier to build a short script, include that in appendices that can be cut and pasted. That'll go out and install the proper packages. This is one of the things we actually did for the very first Veeam paper we did. So the next thing you have to do is you have to understand the product. And just real quick, there are other sessions on Ceph, but just real quick, Ceph is a bunch of individual storage devices associated with software daemons. That's called an OSD. There are multiple OSDs in a single node or storage server, and these all together form RAIDs. The status of each OSD is tracked by the monitor. It just keeps track of whether things are up, down, in, or out. And then you have the interfaces that go out. You have block, object, and file interfaces. There are native and what I like to call traditional interfaces. The native interfaces for block, for example, is Rados block device. Now, what makes a native interface different from a traditional is the native interface uses the protocol all the way to the client. So it has what I like to term a smart client. The smart client, because it uses the native protocol, understands where all of the OSDs are. It communicates with the monitors and gets the map of the cluster. So instead of going through a single choke point to write storage out, it actually does the computations using the crush algorithm and writes to each OSD directly. This makes it far more efficient than a traditional storage device where it has to go through a single choke point. When you get to things like the file interface, you're talking Cephfs is this distributed file system. That's the native protocol. You have NFS and Samba/CIFS that you have for the traditional protocols. From an application perspective, you have the native Rados object protocol that you can use. There are some applications out there that do that, but most of them go towards S3. You have S3 and Swift provided by what we call the object gateway or Rados gateway that can scale horizontally using load balancing technologies. So that's the basics of Ceph. It's a bunch of individual storage mechanisms that hold objects that make up what's called Rados, and it's presented by various protocols. So aside from that, You also have to understand what all the options are. There's a lot of terms that you're going to get thrown around, a lot of things here. Things that you have to think about are your data protection, your failure domains, what kind of storage technology, whether it's an NVDIMM or it's a SATA SSD or a U.2, what version of PCIe is it? Lots of things. You see all these things up here. They're all options, and they're things that you need to think about when you're designing the solution. So let's jump into a couple of those. So which media? We talked about just a second ago. There's NVMe and NVDIMMs and SATA SSDs and all these. You have to determine what makes sense for you. Hard drives, spinning rust, or SSDs. If you're looking at the all-flash, should it be SSD or NVMe? Or if you have the budget, I guess, NVDIMMs. When you're looking at spinning technologies, SATA or SAS, there are some differences. You can actually stack more SAS devices in a single enclosure without oversubscribing. And that's because you can get much faster SAS buses than you do SATA. So one thing to keep in mind when you think about media, Ceph is designed for aggregate throughput, not the low latency I/O operations. At least that's the case today. So really when we talk about NVDIMMs, they probably don't make sense. But once you get to NVMe, they start to make sense, and especially when you move into SAS and SATA SSDs and the hard drives, they make perfect sense. One thing, please, 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 for goodness sakes, do not use consumer devices when you think about flash technologies. Flash technologies in a consumer device are not built for enterprise-grade deployments. They don't have super caps, which ensure that all in-flight data is written on a power-off event. The enterprise devices typically have more spare cells that are in reserve. So when you have cells that are used up, because you can only write to a cell in a piece of flash media so many times before it's worn out, that oversubscription or that extra ratio of cells is higher in enterprise devices. And enterprise devices typically don't make heavy use of things like a small SLC cache to get temporary, very short-term performance boosts. So there are things to keep thinking about there. So some rules of thumb on the storage device: a 7.2K SATA is a bit slower than a 7.2K SAS device, which is definitely slower than a 10K SAS device, which is slower than a SATA SSD, which is slower itself than a SAS SSD, which is slower than an NVMe device. I hope that all makes perfect sense. Now, the next thing I want to give you are just some rules of thumb that I use when I'm looking at storage devices. A few of them that are more common. No guarantees on these, no warranty, no promises at all. Your mileage may vary, but this is my observations. When I'm looking at a 7.2K SATA device, I get around 30 megabytes a second. A 10K SAS device, cluster build of those, will deliver around 45, maybe 50 megabytes a second per device. A SATA SSD, about 120 megabytes a second per device. So if I have a cluster with 100 SATA SSDs, I expect that cluster to deliver somewhere on the order of 10 gigabytes a second. Now that's a plus or minus. There's tuning, there's differences in all the SATA SSDs, depends on your node layouts and a bunch of other things. But as a rule of thumb, it gets you in the ballpark, plus or minus maybe 10-15%. So what about the network? That's also something I like to give some guidance around. If you're still using 10 gigabit, I ask you why. 25 gigabit has come down tremendously in price, and it's got one huge advantage. 25 gig is based on a single 25 gig channel, whereas 10 gig is a single 10 gig channel. That's a difference of 2.5 times faster in the signaling rate. Now you might ask, why does this matter? Well, it's about latency. Every place you can reduce latency in a cluster, you should. Now, I like to bond multiples together. That brings me resiliency and aggregation bandwidth. Now, a single channel, a single client connection is still only going to be limited to 125 gig channel. right? But if I have 100 hosts, they're going to be able to balance across those 4 interfaces, say that's what I've got in my bond, to have the full aggregate throughput. And that's assuming you do things like jumbo frames and a few other things. The other thing I do is I like to use VLANs to segment my traffic and not do physical segmentation. And the reason for this when I'm doing a design is because cabling is great on day one. When it's implemented, it's beautiful, and yeah, you've got those 4 cables, and you know that port 0 on NIC 1 and 2 both go to the public network, and port 1 on NIC 1 and 2 goes to the private cluster network. But fast forward a year, you're maybe not there anymore, someone else is. They have to come in and figure out which one's port 1, which one's port 2. Or worse, they've had failures, and now the cables are going every which way and no longer well labeled. It's just a lot easier if you bond them all together in one bond across multiple switches. Provide yourself protection against NIC failure, against switch failure, and you use VLANs to divvy it up. And again, I prefer heavily 25, 50, and 100 gigabit over 10 and 40 due to the signaling rate of the medium. So let's talk about the network mistake to avoid. Number 1. One of the worst things you can do to a cluster, that's especially if it's a multi-rack cluster, is to have these really well-designed nodes and then not have enough uplink bandwidth from the rack into the core of the network, the core of the storage, the cluster network, right? So if you have, for example, a cluster where every node can deliver, say, 25 gigabits, and you've got 10 nodes in the rack, but you only use 2 25 gig uplinks from the top of rack switches out, you're doing exactly what this picture shows. You're cramming all this traffic through a little bitty, spot, and that creates problems. It's a good idea not to do that. If everyone has their druthers, you don't create a bottleneck at all. Realistically, we know that you can't always get the full amount of bandwidth needed, but try to have as little oversubscription as you can. For example, if you've got a rack with, say, 12 servers in it, and 6 of those would flood, we'll just use 25 gig connections, would flood 2 of those connections, put 4 in, and that should put you at a closer ratio where the chances of totally filling up that available bandwidth is much slimmer. The other thing to avoid is when we talk about jumbo frames. You have to do jumbo frames everywhere or you look like that truck. You're going down the highway, going across the wires, going through a switch, and boom, you hit one where jumbo frames aren't enabled on the port. Your packet blows up. Ceph doesn't work, right? Ceph is actually not designed to deal with fragmentation of packets by a switch that's having to do all the work in the CPU. So this is something to make sure of. And you can check this by doing a 9K ping from every node to every client just to make sure that it all works, or from a client back to the cluster, any node in the cluster probably, once you're sure that between every node of the cluster, 9K ping works. So what about server config? Obviously, we say yes, certified hardware. That's what we want you to look at. That's part of the critical building blocks here. But there are some other things to look at. Consider the PCIe generation and the lane counts. Obviously PCIe Gen 4 slots and devices, you can use less lanes to get the same performance that you would off of PCIe Gen 3 slot and device. This is really important when you start looking at things like NVMe. Also make sure that, say, you're putting in a NIC that requires 16 channels and NVMe that requires 8 and disk controller that requires 16. Hey, guess what? We've already hit 40 PCIe lanes that we've consumed right there. Now, that may not seem like a lot, but if you really look into some of the CPUs that are out there, you can eat up the complete amount of PCIe lanes really fast. And if you take that NVMe and you multiply times 6, now you're in trouble, right? From a memory bandwidth perspective, modern CPUs have 6 banks or 6 channels of memory. Usually it's 2 slots per channel. When you go to build the server config, fill out the memory channels. So if you have 6 channels, you should put in at least 6 DIMMs at a time, 1 in each channel. And that's about getting the maximum memory bandwidth. This does make a difference to Ceph. Ceph uses memory. So make good use of that and make sure that the hardware is being laid out optimally. So what about CPUs? Well, this is where it gets exciting. So here at SUSE, we support both x86 from obviously AMD and Intel and 64-bit ARM CPUs. We've listed a few of them here. So you've got a lot of choices in silicon. Now, there's some general rules of thumb we use around how much CPU you need, and it doesn't really matter that much which one of these processors it is. So for spinning storage, you need 1 2 gigahertz thread per device. For an SSD, 1 to 2 2 gigahertz threads per device. And for NVMe, 2 to 4 2 gigahertz threads per device. And for NVMe, especially if you can get faster, that's better. Because more is always better when you're trying to go faster. Keep that in mind. Now, the metadata servers. So we're kind of digging in a little bit. This is what's used with Cephfs to keep track of all the metadata associated with file system. The more active files you have, the more MDS RAM cache that's needed. And we actually have a SUSE Enterprise Storage performance tuning guide that includes a section that talks about the MDS cache and what variables to check for that. For me, I wouldn't start off with less than 16 gigs. And if you're in a reasonable cluster, you're probably going to be looking more on the lines of 32 to 64 gigs. The MDS really doesn't need a lot of CPU, maybe 4 very fast cores, and obviously the faster the cores are, the better, because this system is serving metadata. And the other thing I would always consider is to put the Cephfs metadata pool on fast storage. By doing this, you're shorting any latency when it has to go, when you have a cache miss. And that really can help performance. So we talked about some of the other traditional protocols where you have gateways. So a Rados gateway can use a lot of RAM and resources. You're talking, in my testing, up to 12 threads 100% consumed, 12 CPU threads, so 6 cores 100% consumed, and around 80 gigabytes of RAM. Now, that's after I've done a little tweaking, to the daemon, but you can certainly see this happen, especially under a heavy load. For other gateways like Samba, iSCSI, NFS, they seem to be fairly light by comparison. Around 16 gigs of RAM, 4 to 6 fast cores is all they really need. And in fact, that may be overkill in some cases. So your mileage may vary on these, but these are the rules of thumb that I work with today. So let's wrap things up. First, you want to match up things between the business requirements and the technical. So business requirements match up to the fault domains, the network architecture. Look at the performance and preference requirements matched up to the hardware selection. Preference maybe being vendors or size of the nodes or power draw or medium. There's all kinds of options there, but those have to be matched up to the hardware selection. So you tie that now to the one above it, business requirements, with fault domains and network architecture tied into the second, which ties into the third, the software requirements that match up the protocols and data protection schemes. With all of these together, you can now start to really come up with a node design that makes sense. And when we go back to the software requirements and the requirements that a particular challenge presents us, this is how we make sure that what we've done makes sense. Have we fulfilled the business requirements? Do we provide the fault domain protection that's needed? Do the software, the third-party software requirements, are they met, in a way that provides all of the business requirements for availability and performance? So again, when we look at business requirements, you're also looking potentially at things like RPO, RTO, data protection, multi-site needs. There's lots of things here. We've already talked about the software with protocol support and performance requirements, just making sure all of those have come in. And at the end, we have a solution design. And that solution design is documented. We produce it, publish it to the website. After we've, during that production process, we've implemented, we've tested, and then we publish. And the important part is maintaining it over time. If this is a document that is utilized by the field, it's always good to know that, because we want to keep those up to date as we move down the road. So real quick, on the SUSE site, we do have hardware implementation guides. If you go to the product page for SUSE Enterprise Storage, on the right-hand side, there is a link that will take you to the reference architectures, and that's where you will find these. We have them there for the hardware, and we also have them there for the software. All right, so it should make it very, very easy. And in conclusion, there's a lot of effort that goes into these papers, and the goal is to make a meaningful impact to you, our customers, and partners. Your feedback's important. Let us know. If there's something that you don't see, if there's information that you need, if the guides are helpful, reach out to your SUSE contacts and let us know. Make sure that feedback gets brought back in, because that helps us understand what's useful, what's not, and if there are applications that you really want to see some guidance for, feed that back as well so that we can put that into the prioritization list. So with that, we're done, and thank you. Have a great day.